Hi everybody. Today is a very special day because in collaboration with Joshua Bardwell and Ryan Harrell, I'm about to bring you the vibration and resonance analysis of the Lumenier QAV-S JB edition. Let's get into it. Okay, so those of you who follow my channel will already probably be very familiar with how this goes. But for those of you who maybe are seeing this type of analysis for the first time, let me take you through how this works. So it starts with Ryan Harrell, who's the designer of the frame. He was kind enough to provide me with the CAD of the frame for this analysis, the digital files that are used to cut the frame in manufacturing. So they have all the geometry, all the shapes, absolutely accurate. I use this CAD as well as models that I've developed for the materials that are used in FPV frame construction, like carbon fiber, the material for the battery, the motors, all of these things. And I use all of that information to build a finite element model of the quadcopter in simulation space. Then Joshua Bardwell was kind enough to provide me with a gyro-scaled black box log from his QAV-S JB edition frame. And I'm then able to compare the results of the simulation against the black box logs from real flights of the QAV-S JB edition to validate the model, and then I show you the results. Let's start by looking at the roll axis. If we look at the spectral graph first, we can see initially we have a big spike at very low frequencies. That's the real movement of the quad in the air, the real flight movement. Then we have a pretty quiet zone up to about 200 Hertz. And this sort of blob here is the first motor harmonics. So as the motors change speed, they have a sort of minimum speed, they have a maximum speed, and at every speed they produce a frequency that is to do with the RPM of the motor. And so we have this sort of blob, which is the first motor harmonic, and there's this smaller blob, which is the second motor harmonic, and there's even a third one as well, which is really very small and you can't see it. We must remember when looking at this gyro-scaled plot that although there is no filtering applied in software, we do have a mechanical low-pass filter that's to do with the soft mounting of the flight controller, and we also have a firmware low-pass filter in the gyro itself at 250 Hertz that is also going to attenuate these higher frequencies. If we look for things that might be frame resonance behaviors, we can see that there's this spike at about 215 Hertz, and that corresponds in the waterfall plot with this sort of vertical white stripe here. And so that's a typical frame resonance, something that we might, we would expect to see in every frame at those frequencies where frame resonances occur. Now these numbers here, these are from the finite element simulation, and they show you the resonant frequencies of the simulated QAV-S JB edition frame. And what you can see is that we do have, and I've highlighted them here, about 5 resonant modes between 193 Hertz and 246 Hertz that are relatively close together and could be contributing to this. So this frame has 5 resonant modes within this sort of 50 Hertz range between 193 and 246 Hertz. And based on my experience of having looked at many different frames in this way, I noticed that when you have a concentration of modes like this, the frame becomes very susceptible to vibrations in that frequency range. And so when the motors hit that certain speed where they're exciting at about 220 Hertz, let's say, the frame really wants to ring along with those motors. And that can create this sort of spike in the gyro signal. If we look now at the D term for the roll axis, we can see a few different things happening. Again, we've got this big spike at 0, which is the real flight movement of the quad. And then we have some of these higher frequency coming in. And in general, my view is that anything below about 100 Hertz for a 5-inch quad, I would regard as good D term. So there are aerodynamic effects, there's prop wash, there's other sources of turbulence that create movement and oscillations at up to about 100 Hertz. And the D term really needs to be getting on the scene and fighting those in order to keep the quad really stable in the air. However, once you get above 100 Hertz, you're no longer really seeing true flight dynamics of the quadcopter, because even prop wash doesn't really occur much above 100 Hertz. So anything above about 100 Hertz I would regard as bad D noise. This is noise from vibrations in the frame, from vibrations of the flight controller, from electrical noise. There's all sorts of different sources, but none of those sources are to do with the real movement, the real flight of the quadcopter in the air. And so they're acting as noise. They're confounding the signal that we want to be looking at and making it harder for the PID loop to do its job. Now, if we look at the D term for the roll axis, we see that we do have two reasonable size spikes, one at about 160 Hertz and one at about 220 Hertz. And it's really interesting. We didn't see this spike as clearly in the gyro traces, but it turns out that it's more visible in the D term. And this is because the D term has an effect of amplifying noise. And these two spikes, one at 160 and one at 220, based on the results of the finite element model, we could see that these spikes might be related to a frame resonance that is predicted to occur at just about those frequencies. And if we look at the waterfall plot, we get some further evidence that it's a frame resonance, because we notice that this band, this vertical band here, doesn't vary with throttle position at all. And if this was a motor noise effect, we would expect it to vary a bit with throttle, because the motors spin faster at higher throttle and therefore should generate higher frequencies. But the fact that it's stable across the whole throttle range really points to us that it's not to do with the motors, it's to do with a frame resonance. Because this plot shows the D term after all the filtering that's applied, these spikes and this high frequency D term noise is going to directly limit the maximum D gain that you can have in your PID loop before you get twitches and hot motors. I know when I have too much D, my quad goes tick, 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 tick in the air. And that sound tells me immediately that my D gain is too high and I'm hearing the noise on the D term affecting the motors. So in order to get the best possible tune, we want the highest possible D gain, because the higher our D gain, the higher we can push our P gains, and that just makes the quad more responsive. But if you continue to increase the D gain when you've got this type of D term noise, eventually you're going to get to a stage where you start seeing these ticks, these twitches and hot motors. Let's look now at the pitch axis. So on the pitch axis, we can actually see this 160 Hertz suspected frame resonance much more clearly. Again, we still have the approximately 220 Hertz vibration that is to do with these 5 modes. And again, if we look at the waterfall plot, we can see that both of these have a sort of vertical stripe nature to them. They occur across multiple different throttle settings, and therefore it's unlikely that they're anything to do with the motors. It's much more likely to be a frame resonance. If we look now at the D term for pitch, we can see that, again, anything above 100 Hertz, to my mind, is bad D term noise, because it's not going to be related to real movement of the quad in the air. It's not going to be related to the flight. It's going to be related to things like electrical noise, things like vibrations of the frame, all of those sorts of things that we don't really want to be looking at with the gyro, because we want the gyro to be focused purely on the actual movement of the quad in the air, because that's what we want to be controlling. If we look over again at this waterfall plot, we can see that at 220 Hertz, there's this vertical stripe, which we now know is indicative of a frame resonance. And this bright area below about 100 Hertz, this is what I would regard as, good D term. This is potentially aerodynamic effects and things of that nature, which we want to be capturing. We want the PID controller to be reacting to. So in summary, we do see that the pitch log, particularly the D term, has quite a bit of noise above 100 Hertz. Because this is happening after all of the filtering, this is going to directly limit the maximum D gain that you can get on the frame, and therefore your overall tune. But obviously we can address some of this with filtering, and I'll talk about that later. I really want to stress at this point that this is still really, really good performance for any traditional frame design. I've got some other videos of some other frames which perform a lot worse than this. So this is still doing really well for a traditional frame design. And you're certainly going to be able to get really fantastic flight performance out of this frame, particularly with the right filter settings. And as I said, we're going to talk about that at the end of the video. Another thing to bear in mind when you look at these logs is that JB was really kind to provide a really long log for me. So this is a nearly 4-minute long log. And when you have a very long log in time, because of the nature of the way that Black Box Explorer interprets the log, you actually see higher levels in all of the spectrographs and all of the waterfall plots with a longer log, all else being equal. So a long log is obviously really great for capturing as much of the behavior of the quad as possible, but it's not the best for making your log look really quiet. A much shorter log will always look quieter than a longer log, and we are today looking at nearly 4 minutes of logging. So we should expect quite high levels of noise across the board just because of the length of the log and nothing else. So yeah, just wanted to stress this is still really good performance. Anyone would be very happy to fly this frame, particularly with the right filtering. So one of the really great things about doing this frame resonance analysis in finite element space, in simulation space, is that we can actually visualize how the quad is moving in the air. And that's what we're going to look at now. So at 160 Hertz, this is the primary resonant mode that is active at 160 Hertz. You can see we've got opposite motors bending up and then bending down. And it's worth stressing that this is hugely exaggerated so that you can see it really easily in the video. The actual movement is sub-millimeter. It's absolutely minuscule. But for the purposes of visualizing it in the model, we amplify all of the displacements by a huge factor so that we can see them easily. If we come over here, this is the results of a harmonic analysis. Now, a modal analysis just looks at a single mode, single frequency. A harmonic analysis combines the response of all of the modes at a particular frequency, in this case 160 Hertz. So if we look at the harmonic analysis, we see that it's really similar to the modal analysis. And what that tells us is that really only one mode, this 160 Hertz mode, is important for the harmonic response of the quad at 160 Hertz. And this final video shows you a stress plot. So this is showing you the stress in the arms as a result of the vibration. And what this tells you is where material could be added to increase the resonant frequency. If you add material in the locations which are showing the most stress in this plot, you will have the most effect at increasing the resonant frequency. And for this particular mode, we can see that it's the arms where we need to add material, and it's the top and the bottom of the arms. So if you were to make the arms slightly thicker, maybe go to a 6mm arm, you would have the maximum effect on that 160 Hertz resonant frequency and push it to a higher frequency and also reduce its amplitude at the same time. If we look now at the response at 214 Hertz, which is that second spike that we saw in the spectrograph, it's a lot more complex than the first one. There are 5 modes that are very important that I've picked out here, and these occur at frequencies between about 194 Hertz and about 246 Hertz. The simulation never quite perfectly matches the black box log, but if we get to within 5%, we can be really confident that the simulation is behaving in a similar enough way to the real quadcopter that we can draw useful conclusions from the data. So if we look at these 5 resonant modes, we can see that at 194 Hertz, we have a mode where all of the motors are moving up and down together, and the whole quad is kind of bouncing up and down. If we then look at 222 Hertz, we can see that we have a mode where the motors are rotating in torsion on the end of the arms. And if we look at the other modes, 228, 236 and 246, we can see a similar thing, that all of these modes involve the motors twisting on the ends of the arms. And actually, this torsional flexibility of a traditional single arm is a cause of a lot of the resonance behavior of traditional quadcopter frames. And even though this frame is an excellent example of a traditional quadcopter frame design, it still has this particular behavior. If we now go over and look at the harmonic response, we can see that the harmonic response really looks a lot like the 222 Hz mode, with just a little bit of the other modes kind of mixed in. And that's quite typical of what we see with a harmonic response. It's usually dominated by the mode shape that's closest in frequency to the response, but there's all the other modes, not just the main 5 that I've picked out here, but all, well, 30 modes was the number of modes that I generated for this frame. All 30 of those modes, all the responses are combined together to create this harmonic response. So it really is as close as we can get in simulation to the real movement, the real vibration of the quad in the air, albeit hugely exaggerated so we can see what's going on. If we look at the stress plot as well, we can see that again it's the arms where the maximum stress is, and we can see that that peak stress is occurring really at the edges, the corners of the arms. So if we were to add more material to that arm, making it slightly wider or slightly thicker, we could improve the stiffness of the arm to the torsional modes. And again, if we were to make the arm thicker rather than wider, we'd also have a positive effect on that 194 Hz mode where the arm is bending up and down. And if we look at the yaw axis, I mean, there's nothing to see here really. It's quite typical of well-designed frames that have been built with care to have very quiet yaw axes, particularly on relatively stock Betaflight settings. And so I'm not really surprised that there's not much to talk about here. So moving swiftly on. So with this new understanding of the overall performance of the QAV-S JB edition frame from a vibration and resonance standpoint, we can actually use this information to make some filter suggestions for this particular build. And the first suggestion is to try disabling all the gyro low-pass filters, because they really don't seem to be helping very much on this build. There isn't a lot of high-frequency noise that really needs to be attenuated by these gyro low-pass filters. And if we can turn off these low-pass filters, we can actually save some phase delay. And saving this phase delay allows us to use it elsewhere to further improve the performance of the quad. Secondly, make sure that the dynamic notch and RPM filters in Betaflight are both able to drop below 160 Hz so that they can take care of that first frame resonance. That's really important. And thirdly, consider disabling the dynamic D-term low-pass filter and replacing it with a static PT1 or Biquad filter with a cutoff around 100 Hz or perhaps a little bit higher if possible. Now, dynamic D-term low-pass filters, they move in frequency with the throttle position. And what we can see from the black box logs that Joshua has provided is that the D-term noise is not moving with throttle position. It's a vertical band in the waterfall plot. It's not moving with throttle position. So we don't want our filters to move with throttle position either. We want them to stay static so that they're doing a really good job of cutting out that noise across every throttle position. So if we replace those dynamic filters with a static, either PT1 or a Biquad filter, I tend to prefer Biquad for D-term because it's just that little bit more aggressive. And we pick a cutoff of around 100 Hz, we should be able to take care of both the first and second frame resonance noise on the D-term. And that will allow us, hopefully, to push the D gains a little bit higher and therefore push the P gains a little bit higher, and therefore get an overall more responsive quad that's even more enjoyable to fly than I'm sure it already is. I hope you found this analysis of the vibration and resonance performance of the QAV-S JB edition interesting. I particularly hope that it helped you if you're trying to decide whether this frame is right for your next build. If you've never seen anything like this kind of analysis of a quadcopter frame before, welcome to my channel. I have quite a few videos on various technical aspects of FPV motors, props, and frames. I hope you enjoy them. I hope you find them useful. If you'd like to see how a different frame performs, I'll put a link to the analysis of my frame, the AOS 5, in the description below. I haven't got any more for you for today, so until next time, all that remains is to wish you all very happy flying.